Okay, the last section of chapter 10, we are comparing linear, exponential, and quadratic models. When you look at these words, linear, exponential, and quadratic, they all are addressing what's happening to the input. Which letter is the input in equations? X, right? Now we know that's arbitrary. We could change it and have G, H, or P, Q, or whatever, but usually we have Y and X, right? The input is X. So when we have a linear function, what is happening to the X? What is the exponent we're raising it to?
To the 1.
To the first. Let's say our favorite form of a linear function. Y equals
mx plus b.
Very good, mx plus b. Okay, so that x is being raised only to the first degree, right? And so that's where we say when an input is to the first, it's linear, okay? Write that down underneath the word linear. Y equals mx plus b. You can write that down. I'm not changing things because I will reveal too much at one time if I do. Exponential. What is happening with the input for an exponential function?
Multiple.
Where is the x in an exponential function? It is the exponent, isn't it? That's why it's called an exponential function. The input is the exponent, which is really different than these others. Okay? Because the quadratic is more like the linear. What is happening to the x in the quadratic? We're raising it to the second, which is why I wish it was called squadratic. But oh well, it's quadratic. Okay, so here we have the different function forms of these equations that you've worked with. So really pay attention to what's happening to the x here. X to the first, the x is the exponent, and then x to the second. Okay, so what does a linear equation with your arms? Show me a linear equation. Good, everybody is making a nice line. And with your arms, show me an exponential equation. No, that was more quadratic. It's kind of like this. It's like a pretty ballerina, like this. Okay, and then quadratic, show me with your arms quadratic. It's almost like scoring the football touchdown. Okay, so here we have kind of a generic look at the functions that you have graphed. What we're going to identify today is if you are, well, number one, if I gave you a graph like this, could you quickly say, oh, exponential, quadratic? I think you could, right? So you will do a little bit of graphing just to make sure that you have the connection between equations and graphing, quick graphs. But then what about if it's in a form of a table or you're given a series of points? This is more interesting. We all like to get to our answer without graphing because it's usually quicker, right? So we're going to use this equation, y equals x plus 2, to identify what is happening with all linear equations. Okay? So let's make a little table. What values would be good to place in the table? Just one.
-2, -1, 0, 1, 2.
Good. Okay, so when we plug in, let's start in the middle. When we plug in 0, what do we get?
2.
Michael, when we plug in 1, what do we get? And 2? And -1? And -2. Okay, so we have placed our domain, the x values, in increasing order. So we have this beautiful pattern in the domain, right? So now what we're doing is looking at the range. What is going on here between each of these values? Jack says we're adding 1, adding 1, adding 1, adding 1. So when we see constant addition, what type of equation do we have?
Linear.
Linear. Could I also say when we see constant subtraction?
Yes.
So if we were to go the opposite way, isn't it -1, -1, -1, right? So addition or subtraction give us linear equations. And so here we have the rule for this. The first difference in the y values is the same. A difference of 1, a difference of 1, a difference of 1, a difference of 1. This is key that you place this rule down. It's the first difference in the y values. Okay, with our exponential function, we had some interesting important details to the rule. I mean, the basic exponential function is y equals b to the x, as though a is 1, right? So here's our model, but we could just bring it down to 1 times b to the x. B may not equal 1. What would happen if b was 1? Do you remember?
Everything would be 1.
Right, because 1 to the first,
1,
1 to the second, 1 to the third. So what kind of equation do you get when you graph that? Y equals 1. Show me with your arms, where is that? Y equals 1. Very good, horizontal, right? All the y's are 1. So that would wipe out the exponential interesting feature there, right? Also, b may not be negative. Do you remember what would happen then? Let's try negative 2. So if b is negative 2, what is negative 2 to the first?
Negative 2.
Negative 2. And negative 2 to the second? Negative 2 times negative 2 is 4. And then negative 2 to the third?
The opposite is
Negative 8. And negative 2 to the fourth? 16. So we have this thing back and forth, never touching 0. So it hops over 0, hops over 0. Very strange thing. Not an exponential function. Okay? So we're limited to a b value that is greater than 1. So I'm going with this one here. Y equals 2 to the x. It's the smallest integer we can plug in for b. And when we plug it in, we can, may we use negative values in our domain? Yeah, we can, sure. Negative 2, negative 1, 0, 1, and 2. You may. Let's start with 0. What is 2 to the 0?
0.
2
2 to the 0 is 1. Okay, 2 to the first. 2 to the first. 2. 2 to the second.
4.
4. Now what happens when you have 2 to the negative 1?
Half.
1 over 2, very good, 1 over 2. And 2 to the negative 2?
4.
1/4, good. Okay, so we're looking for what's going on in the range. And very
Times two.
good. We're multiplying by
We're doubling.
2. We're doubling, multiplying by 2, multiplying by 2. Or if you look at it in the reverse, we're dividing by 2, dividing by 2. Okay, so when you have constant multiplication, you have an exponential function. Ratios of successive y values are equal, or you have a constant factor. Okay? So in the ratios, what that means is 1 over 2 equals 2 over 4. Right? Ratios are equal, or you could say I have a constant multiplication, times 2, times 2, times 2. That is the same as a constant ratio. Okay, finally with our quadratic, we're looking for what is this pattern, this important pattern that you could find in the range. Okay, so when we plug in values here, is it all right if we use negative values? Yes, so negative 2, negative 1, 0, 1, and 2. Okay, so we're using this parent equation here, the most basic quadratic equation, y equals x squared. Really little, basic, doesn't have a lot going on, there's a square there. So when you plug in 0, what is 0 squared?
0.
And what is 1 squared?
1.
And what is 2 squared? But what is negative 1 squared?
1.
And negative 2 squared?
4.
Good. So we see that symmetry that we're used to seeing, right? And if I saw a table like this, I'm sure if you saw a table like this, you would say, oh, symmetry, quadratic. It looks quadratic, right? Because you've seen a few of these, and you've created a few of these. But let's see how else you might look at this. So we have our constant increase in the x. So let's look at the difference in the y. What is 4 minus 1?
3.
What is 1 minus 0?
1.
What is 0 minus 1?
Negative 1.
And what is 1 minus 4?
Negative 5.
So do you see, it looks kind of parabolic there too, doesn't it? I mean, you see the same thing? Let's see, what is 3 minus 1?
2.
What is 1 minus negative 1?
2.
What is negative 1 minus negative 3?
2.
What the? Do you see this? So when you take, this is called not taking the first difference. This one over here was the first difference, right? But when you take the second difference here, you see a constant second difference, and that's a quadratic equation. Okay?
That's so cool.
So here you go.
Crazy.
The pattern is in the second difference of y values. And I mean, honestly, you could go graph it and see a parabola, but you might save yourself time by just looking at the second difference.
Or just not.
Okay, so this looks different, but it's the same question. Can you identify the function? So today in your assignment, you'll be asked to graph. And I want you to, because listen why. You need to continually imagine what these things look like on a graph and what they look like in an equation. You may receive them three ways: as a group of points, as a graph, or as an equation. And you need to continually kind of review that. But do we see, without even graphing, do we see an increase in our x values that's constant? Okay, so they've already set this up in perfect order. Now if I wanted to make this tougher for you, I would move these points around so they weren't in perfect order like this, right? But since they are in order, do you see a constant change in the y value? What is the constant change? Multiplication of? So what is this equation? Exponential. Good job, Jack. Way to go. Okay, so here we have the exponential function, and Summer beautifully put it in the form of an equation, which is just an extension for brilliant people right there. Okay. Let's try it again. Now, everyone quiet. Take a look at this, if I can get it to work, and we will see. I want you to analyze the points right now, even without your graphing, and then ultimately graph it. But shh, quiet. Your first question is, are the x's in order increasing left to right? Okay, if they are, then look at your y values. And when you look at your y values, what do you notice?
Linear.
And you think it's linear because what do you see, Sydney?
Increase.
What kind of an increase?
Adding.
Adding. So adding what? So you're plus 1. Plus 1. So we have linear. And can you write the equation? Since Summer did that on the last one, let's see if anybody can do it on this one. Kelly.
So it would be y equals x plus 1.
Good job, plus 1. Look at, here's your y-intercept. Did you do that? Remember how to find it? So excellent. And then of course you could graph this. So 0 is at 1 and it's a slope of 1. So, you know, you can do it better on paper than I can do here. Okay? And probably, because I want to be thorough and giving you samples. When you look at these numbers, shh, quiet. What do you see? Did you find the second difference, or did you just see the symmetry?
I looked at the symmetry. First, actually, I looked at the x values and saw that they were in order, and then I looked at the symmetry.
Okay, so you can see the symmetry so clearly, but if we were to find the second difference, the difference here is 2 minus 5 is negative 3, 1 minus 2 is negative 1, 5 minus 2 is 3, 2 minus 1 is 1. The second difference is what?
Minus.
It's the same as the one in our sample, right? 2. So you would graph, and oh, could anybody write this equation?
No.
That's a good question.
Ultra.
Okay, what is it, Jack?
Y equals. My phone, you can
Y equals AX squared plus BX plus C.
What is the y-intercept?
You're just
Y
Good job, there it is. Now, you're not even being asked to do that, but it wouldn't be bad for you to try. Excellent. And there you go.
That's it.